All right. Welcome to, apparently today is officially midterm. I will be grading all this stuff today, getting grades in for midterm grades so I can give you a sense of where um, that, um, where you are. You can look at your grades to see past homeworks that you have missed. Um, Again, I just really want those to be completion grades so that you don't get hurt in the end. The tests are worth 14%. The homework itself is kind of like a fifth test, so it's the final 14% of the grade. So if you don't do any of it, it's like just throwing away one of the tests. So please don't do that. So that'll be in there. Schedule-wise, we skipped one of these sections. I think I sent an email about it. Days are kind of running together here, but 6.7 we skipped. We're going to do that today along with 6.8, which is good because they kind of go together anyway. And so we'll do that. We'll see if you have questions about anything, and then we'll go on from there. Okay, so 6.6, 6.7, and 6.8.
So 6.6 is due today and 6.7 due tomorrow, along with 6.8.
Yeah, so we're just basically pushing that one section back. Originally due today, but due next time.
So, sir, did we do 6.6 last time we met?
Yes.
Okay.
It was a sort of a cursory approach to it because the hyperbolic functions, we didn't spend a huge amount of time on it, and we'll see if there's questions, and maybe we can review some of that stuff as well. Yeah. Okay, so this is where things start to get a little strange with numbers. You probably could say, let's see. So let's look at these values here if we can. So if I just said, hey, what happens if you take a number and raise it to the 0 power? Probably remember what that is. And so that's raise a number to the 0 power. Usually you're like, okay, well, yeah, that's 1, right? So 0 power gives you 1, which is initially like, that feels weird. 0 causes problems. It helps sometimes, but it causes problems in others. So you have that. But then you're like, well, okay, what happens if I take 0 and raise it to a power? It may not be the same one, so maybe, but I'll still use them. If you take 0 and raise it to a power, you're like, well, that means 0 squared is 0, so 0 times as many times as you have is 0. So then the question is, well, what happens if you try and combine those? And the question is, what is 0 raised to the 0 power? Well, according to the first line, it says the number is raised to the 0 power should be 1, but the second line says that 0 raised to any power should be 0. So how do you combine those into 0 raised to the 0 power? That's a good question. So what is that equal to? First line says it should be 1. Second line says it should be 0. So that's going to be a problem. Come back to that. You're also not supposed to divide by 0, of course. But what happens if you take 0 and divide it by 0? Well, your brain might be like, well, any number divided by itself should cancel out and give 1, right?
Which means it's nothing divided by nothing, so it's still 0.
It's still what?
Still 0. It's nothing divided by nothing.
Oh, okay. Well, let's see. What about a number divided by 0?
That's going to be nothing because it's nothing going to a number.
So wait, if you take a number and divide by 0, what do you think that means?
0.
Error.
Divide by 0?
Well, I mean,
It'll be like an error. It doesn't exist.
Yeah, so I mean, you think about it, what does it mean to divide? It means what number do you multiply by 0 to get n? Like how many pieces are you breaking n into?
you can't. Oh, you can't. Yeah, I get it.
Okay, right, so that's undefined. Whereas 0 divided by n, that is 0. So if you divide 0 by a number that's not 0, you get 0. If you take a number and divide it by 0, that's undefined. Now make it even worse. Divide 0 by 0. You might say, well, the answer is 1 because they cancel out. But I could also divide 0 into two parts, 0 and 0. And they both come together to give 0. So maybe the answer is 2. Maybe the answer is 50. I don't know. So
the answer could be undefined or 0 in this instance, right?
So the answer, I'll tell you in a second. So because I want to do one more, and there's actually a bunch more, but we'll just start with these, is what happens if I take infinity and divide it by infinity? I don't even know what that means. I mean, what do you mean when you multiply infinity times a number? It's sort of even worse. So all these things, 0 to the 0, 0 divided by 0, infinity divided by infinity, are not quite undefined. And we'll show you why. I'm going to put quotes around because I really don't like writing any of these things because they don't make any sense. These are all called undetermined or indeterminate form or indeterminate forms. And so they're not quite just straight up undefined. There may be like some meaning behind what do you really mean by 0 divided by 0? Or what do you really mean by, you mean 0 or do you mean like something really close to 0? And the same thing here. Do you mean infinity or just mean something that's really big divided by something else that's really big? We're going to delve into these things. That's why I put quotes around. It's like we don't really mean 0 to the 0. So here's where it's going to start to arise from. We can talk about limits, and this is exactly this section 6.7. I'll tell you the name on it for a second. So the limit of something that looks like this. Limit as x approaches 0 using only positive numbers of sine of x divided by x. So if you were given this problem back at the very beginning and you didn't even know about plugging in numbers or anything, what you have to do is you have to make a table of values where x is getting closer and closer to 0 using positive numbers. So that means I take something like, well, something close to 0. 0.1 is pretty close to 0. And I substitute that in, and I just use my calculator, and I calculated it out. This is approximately 0.998. Okay, that's the first starting value. Then I take values that approach 0. They get closer and closer to 0. So this is 0.1. Take another number that's even closer to 0. So like 0.01. So that's getting closer. I put that in my calculator. It says 0.99. It actually says 9999 before it starts to get something else. Okay, that seems to suggest something, but if I tried one more here, 0.001, values that are getting closer to 0, but from these positive values. Then the same thing here. This is like 999999. Okay, where is this going? It really looks like the answer is 1. And that, in fact, is true, that the answer is 1. If you plotted this on your calculator, y equals sine x divided by x, it would look approximately, the calculator would look approximately like this, and I'm just going to leave this off for a second. Now, if you really zoomed in on the table on your calculator, you realize it comes up, there's a little hole here, and then it continues along. And the reason why is because you can't actually stick 0 in. You can't sub in 0, x equals 0. Why not? Well, what happens if you stick in 0 in here? Then it looks like you would have sine of 0 divided by 0. I'm going to put that in quotes too because it's still not good. You're dividing by 0.
And no number multiplied by 0 can ultimately result in that filling that void where sine of 0 is.
What is the sine of 0? just the sign of 0 by itself?
1.
Nope. The other one. Sign of 0 is 0. So this looks like I have 0 divided by 0. Now, I didn't say that was undefined. I said it was indeterminate. So in order to determine this particular 0 over 0, I look at the table. And as I get closer and closer and closer and closer and closer to 0 for x, this thing gets closer and closer and closer and closer to 1. And so I'm at height 1. So in this case, 0 over 0 in quotes sort of resolves out to be 1 in this case. In this case here. But not always. Not always. Let me try one more example, and then we'll just sort of knock it out of the park. You can say, well, what about this? Limit as x goes to, what's an example here? Well, we'll just do this. X equals 0 to x over x squared. It's a very basic example, but it'll give us some sense of what's going on. So if we plug in 0, we just try and sub 0 in. Then the top would be 0, the bottom would be 0 squared. So that looks like 0 over 0 again. So it's got this 0 over 0 indeterminate form, is how you say that. But what happens as you plug in numbers that are getting closer and closer and closer to 0 for this one? Well, it turns out that we've done this one before, but since x is not actually 0 yet, it's a limit, so it's getting closer to 0. So if I have x divided by x, I can use it to be 1 as long as x is not 0. And in the limit, it's not. So it looks like the limit as x goes to 0 of 1 over x. Now, what is that? Well, I can't plug in 0, so I need to make a table here of x and 1 over x. Take numbers that are close to 0, substitute them in, and let's see what happens. So if I plug in 0.1 as a starting point, plug that in and take the reciprocal, I get 10. Because this is 1/10, reciprocal is 10.
I'm just curious, though, why exactly should you need to do that? Because ultimately, you still can't input 0 into 1 over x.
Right, but so I can't put it in to look in the last problem. I can't plug it in to sin x over x anyway, but I can get close.
But could you still get close with the function you still had?
This one?
No, the previous one. The one, yeah, that one. Couldn't you still gotten close with the x over x squared?
Well, so if you just try to, if we didn't even simplify it down, then if I plug in 0.1, this works out to be 10. If I plug in a number that's closer to 0, this will work out to be 100. If I plug in a number that's getting closer to 0, it'll work out to be 1,000. These numbers are going to 0 from the positive side. Where is the right-hand side going towards?
It's going to the positive side as well.
Yeah, but what number is it going towards? What number are these going to? 10, 100,
Infinity.
1,000? Yeah, so plus infinity. So that is, we would say, the limit as x goes to 0. From the plus side is plus infinity. How about if we use values where you're going the limit as x goes to 0 from the negative side? Well, if we do it from the negative side, this table, all of the x's will now be negative. Here, negative 1/10, negative 100, negative 1,000. Take x over x squared, you'll get negative 10, negative 100, negative 1,000. These numbers are going to 0 from the left side. Where is the resulting values going? These are going to negative infinity. So I'll get negative infinity. So I basically get no limit, because half the time it's going to infinity, half the time it's going to negative infinity. And if you were to plot this function, it looks like this. It comes down. It's the reciprocal function. So that's my graph there. And in this case, I can't plug in 0 over 0, and the reason why is because in the graph, there's not a hole like last time, there's actually an asymptote there. And so I can't resolve out what this really kind of 0 over 0 would mean.
So it would just go into infinity. That's a problem, though. It's not going to actually come anywhere near trying to approach a value.
In this case, that's correct. Yeah.
So would you? Okay.
It's not even going to 1 infinity. Half the time it's going to positive infinity. Half the time it's going to negative infinity. So it would end in the end to say that this limit does not exist. Okay. Even though, we try again, we plug in 0, we get 0 over 0. In the last one, it resolved out. It did resolve out to be 1. In this case, it doesn't resolve out at all. So when does 0 over 0 resolve out to be something, and when does it not? That's the question we're asking.
Okay.
So
I was also you didn't exactly did you exactly define indeterminate form? Like, did you get an exact definition? Because if so, I didn't hear it.
yeah. So well, undefined is one thing. It means that it is just straight up does not exist.
Okay.
0 over 0 is not really something you can do, but the 0 over 0 will arise not necessarily just from taking 0 divided by 0. It could be like, what happens if I did 0.000000001 divided by 0.000000001? It looks like it's really close to 0 divided by really close to 0. But in this particular case, that's 7, 8. This answer is 10. So it looks like something really close to 0 over 0 resolves out to be 10. So when I write 0 over 0, it'll come from a limit when you just plug things in. But if it's in a limit, you shouldn't have plugged things in. You should have worked it out another way and actually gotten an answer. So this trying to plug in leads to these things. And really defining what indeterminate form is difficult. I think it's just to come up with a list of things that will arise. We put them in this category called indeterminate because we could use another method to determine what they are, is the idea. We can't just straight up say it doesn't work. We have to go back and do more work to figure it out.
So you don't have an exact definition, but I didn't entirely understand your example. So you just say it's something that can't feasibly be performed for a function?
Okay, let me just try another example and we'll see what this means. So
Okay.
suppose we did this example here.
Okay.
What's the answer?
Can't think of it off the top of my head because it can't be 0. You have to approximate to it.
Approximately what?
You have to approximate to it. I mean, you're gonna get closer and closer to 0 with x, and you're gonna have to closely approximate to it. You can't just put 0 in, or else it won't be defined.
The top is not 2.
Cosine n x is 1. Minus 1 will be 0. And you plug 0 in for x, will make it 0. So it'll be 0 over 0.
Right. So if you just try and substitute it in 0, it doesn't work.
Yeah, that's what I'm saying.
Okay. But does that mean that there's no answer at all?
No.
What?
No, it can still be approximated to.
We could end up getting an answer. If we plugged in 0 and we got 1 over 0 as my answer, that's purely undefined, and the answer would be not defined. If we plug it in and we get a form, if we tried to substitute in, if we get a form that looks like 0 over 0, that's not the end of the road. It's possible that if we did it by another method, we could get an answer. So the subbing in method doesn't work. But it's possible that another method does. So if we see a 0 over 0, that just means we need to go back and try something else. That's the best I can sort of say right now. And at this point, the best you can do is just try and plug in numbers that are really, really close to 0. So if I substitute in numbers that are really close to 0 into this fraction and worked it out, it turns out all of the answers are really, really close to 0.9999999.
Okay. So in the term, sorry.
Yeah.
I was saying, so in the term, this is basically just approximate. Is this basically when a function has to be approximated to? Pretty much all it is.
I would say that. That works out.
Okay.
And sorry, it's not, no, let me get it right. I have to then go back and think about what this is. It's the answer, sorry, the answer in this particular case is 0. This one is 0. This one does work out here. By just subbing in points for x that are really close to 0. And when you say approximate, that's true. It's approximate, it's approximate, it's approximate. But in Calc 1, we said if you take the limit, you do actually get to 0. The limit is 0. We never get there like at any specific point, but the limiting process like is 0. So same thing with, you know, if you just did the limit as x goes to infinity of 1 over x. What does that mean? That means that x is getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. What happens when you take a reciprocal of big numbers? They get really small. So this number is getting really, really small, 0.01, 0.001, 0.001. Every single one will have a little bit of a fraction to it. But the limiting process, where is it headed? That's 0. That is equal to, the limit is 0, even though you're never exactly at one of those points. And that's just a concept from Calc 1 that you kind of have to get into your head. And that's the same thing here. The limit is 0. Well, how did you know that? Well, I plotted some points and saw it. Okay, well, you didn't show them. I know, but I don't want to write all this out right now. So instead, this is the method from 6.7, and it is a specific rule. It's by a French dude. His name is Lhopital. That's how you pronounce that. It's like Lhopital, but it's Lhopital. This little thing called the circumflex, and this is called Lhopital's rule. What it says is if you have a limit, if the limit as x approaches some value, I think the book uses a, of one function divided by another function, has the indeterminate form. So if you like, just in the ones we just did, if you try to plug in your value and you get indeterminate form, has the indeterminate form of either 0 divided by 0 or infinity by infinity. I'm going to go ahead and just erase this stuff. If it has that form, either one of those, then what you can do is that this limit, you'll get the same answer if you compute this limit. The limit as x goes to a, where it's not quotient rule, but it's just the straight up derivative of the top divided by the derivative of the bottom. So in cases where you try and plug these things in, you get 0 over 0, which we've seen, or infinity over infinity, which we will see. That to work, instead of going back and doing a table, the shortcut called Lhopital's rule is you take the derivative of the top, the derivative of the bottom, and then recompute the limit. And if that gives you the answer, then that's the answer to the original problem. So this is the rule. We're not going to prove it. We're just going to demonstrate it through several examples. So for the example we just did, the limit as x goes to 0 of cosine of x minus 1 over x. So that's the one we just did. If we try and sub in x equals 0, this leads us to 1 minus 1 over 0, or 0 over 0. And so that's, in Lhopital's rule says, if you try and sub it in and it leads to 0 over 0, then you can do this trick, or this rule. The Lhopital's rule says that you can do the same limit, but not applied to what you had. It's the derivative of the top divided by the derivative of the bottom. So if I take the derivative of the top of this guy, the derivative of the top will be minus sine. And if I take the derivative of the bottom, I get 1. So I would then recompute this limit with these two new guys, sine of x, negative sine of x, and 1, and now recompute. So what do I get if I try and compute it now? Well, in fact, recompute by just subbing in x equals 0. But what happens if I plug in x equals 0 now? I get negative sine of 0, which is 0, divided by 1. What is 0 divided by 1 now? That answer is 0. We've already seen that 0 divided by any non-zero number is equal to 0. So this idea of doing L'Hopital's rules, as it's called, taking derivatives of the top over bottom, recomputing, we end up being able to conclude that the limit as x goes to 0 of cosine of x minus 1
So
is 0.
it's a way of finding the absolute or the definitive value of any indefinite form.
Those two indefinite forms, 0 over 0 or infinity over infinity. Yes.
Wait. So it can't be for. Are there any other indefinite forms that? I'm asking a lot of questions. I'm sorry. I'm just kind of curious.
That's fine. These two forms, you can use L'Hopital's rule. There are many other indefinite forms that you cannot use L'Hopital's rule on, which stinks. However, you may be able to, in a sneaky way, take another indeterminate form, do some algebra, and transform it into one of these two. Then you can use L'Hopital's rule on that. And I'll show you definitely some examples of that. Okay, so there we go. We didn't have to make a table anymore, which is good, because making tables is annoying. It takes too much calculation time. Although it's a good idea if you don't understand what's going on. This really just means plugging values close to 0 and see what this fraction is. And sometimes it's a good idea just to go back and do that. Okay, so here we go. Example, limit as x goes to 0. Exponentials are feeling left out, so we'll put this in. E to the x minus 1 over x squared. Okay. So we do have to confirm that we have the indeterminate form that we think we have, so that we could use L'Hopital's rule. So do we have the correct one? So we try to sub in x equals 0. And if it works, that's the answer. And that's the nice thing about limits. If you can substitute it in and get the answer, then that's the answer. If not, then fooey. So try to stub in x equals 0. So we do that. E to the 0 minus 0 minus 1 all over 0 squared. Now, does that give us our indeterminate form? Well, e to the 0 power is 1. So e to the 0 is 1. So I have 1 minus 0 minus 1. We do get 0. And 0 squared is 0, so we do get our indeterminate form 0 over 0. So this means that L'Hopital's rule applies. If you don't check this and you just try it, you might get lucky, but you might also run into issues as well.
Is there a rule when using L'Hopital's rule of how many derivatives you can use?
No. Well, I mean, there's no limit. There's no limit. So, and
So you could take the second, the third, the fourth derivative?
Yeah, because really what you're doing is you're pretending like you're just starting again from a brand new problem.
So you could have the first, like, f of x be third derivative and g of x would be the second derivative, and that could totally work as long as the value is no longer 0.
They have to be the same derivatives. So
okay,
if we do the derivative of the top, what do you get for the derivative of the top? Well, e to the x, that's the same. What's the derivative of this is minus 1, and the derivative of 1 is 0. So we do a derivative there, and we do a derivative on the bottom. We just get 2x. And then we repeat. we see, can we do this limit answer? Well, it's just like in the last chapter. We tried to do something to make it easier. Did this make it easier? Well, if it was easier, then I should just sub in x equals 0. So we try that. Try to sub in 0 now. We get e to the 0 minus 1 over 2 times 0. Just sub in 0. What do we get now? Oh, crap.
Now it's still 0 on the bottom.
You get 1 minus 1, so 0 on the top, 0 on the bottom. So we're not done. we ended up from one indeterminate 0 over 0 to another indeterminate 0 over 0. But if you look at the fraction, it does look easier. There's less terms on the top, and there's a lower degree power on the bottom. So this is a case where it's an iterative process where you do L'Hopital's rule again. And yeah, I mean, technically it's the second derivative and second derivative from the first one. I just think it's easier just to do it one at a time. So that, pretend like that first problem wasn't even there and you're just calculating this new one. It worked out to be 0 over 0, so I use L'Hopital's rule. So I take the derivative of the top and then the derivative of the bottom. So derivative of the top is e to the x, derivative of the bottom is 2. And now I try again. So I try to sub in x equals 0. And what happens now? I get e to the 0 divided by 2. And that answer is a half. Good. All these things are equal signs. So if I wanted to go back to the very beginning, the limit as x goes to 0 of e to the x minus 1 over x squared is a half. All these things are equal. So let's take the first and the last. So I had to do L'Hopital's rule twice, but in the end, it gave me my answer. And if I was to plug in values that are really, really close to 0, this would work out to be like 0.4999999, which is really close to 0.5, which is a half. And the limiting value is a half. So that's how you do that. Keep going here.
Why didn't we learn this earlier? It seems really helpful.
Yeah, you know, delayed gratification here. You keep all this like secret stuff and just go, oh, well, this is so much easier.
Teach you all the hard stuff first, and like, if you actually learn, you can actually use it easier.
That's right. It's a present. You get a little present. Okay.
Work for it.
You gotta work for it, man. You gotta put in your time. Okay. How about this one? So we have a polynomial divided by another polynomial. And there are probably a couple ways to do this one. You can make a table, but in this case, when you put in a table here, I'm just going to write out a couple of examples. Fraction, whatever that is. I'm now letting x go towards infinity. So you're going to want to plug in big values, like, I don't know, plug in 1,000, then plug in 10,000, then plug in 100,000. So 10 to the 6, 10 to the 7, 10 to the 8, and let those go. And then the question is where does this go towards? And you can plug it in, and when you do, you're going to plug it in. You're going to get numbers like 0.3334, maybe, for example, and then the next one might be 0.33333332. And so you work this out, and you're like, it really looks like it's going to 0.33333333 repeating, which is a third. And so if you did the table, that would be your guess here, is that the answer would be a third, just by plugging in values, straight up. But now, yeah, let's try our indeterminate form. And so now, what do you mean now? Well, I'm going to let x go towards infinity. So just look at the top there. If you were to say, if x is getting really, really big, what would happen to just the top? So, well, I've got an x squared.
It'll get infinitely bigger.
Well, it's doing what?
Infinitely bigger.
Yeah, why?
Because it is, the first term is squared.
Mm-hmm. Right.
And it is equal to the denominator, which its highest value is squared too. Therefore, it will continuously get hit bigger.
Okay, so just the top by itself, yeah, this is where you start to look at like terms. Which one is really bigger? You know, they're both big. If I put in a million for x, this would be a million. But a million squared is, you know, this is like 10 to the 6th versus 10 to the 12th. That's massive. That's a gigantic number. What is that? Like a quadrillion minus a million. It's like quadrillion doesn't care if you take away 1 million. It's nothing. So the top looks like it's going towards infinity. Top's getting really big. At the same time, the bottom is also getting really big as well. So we have now our infinity over infinity. Let me know if I freeze up because my thing goes unstable once in a while. So it looks like I have infinity over infinity if I was just to look at them separately. So this is the second indeterminate form. That I can use Lhopital's rule on. So we try that. So Lhopital's rule says that if I get an infinity over infinity indeterminate form, I can take the derivative of the top divided by the derivative of the bottom and try again. So if I take the derivative, I will get 2x minus 1 on the top. This is not quotient rule. It's just straight up derivative over derivative. And the bottom would be 6x plus 1. And try again. So what happens is to the top as you put in numbers that are getting bigger and bigger and bigger. Well, it's 2x. So it's going to be getting doubly bigger and bigger and bigger. The top's going to get really big. If you plug in really big numbers into the bottom, it's also going to get really big, which looks like you have a really big number divided by a really big number, or the infinity over infinity indeterminate form. So you can do Lhopital's rule again. So Lhopital rule for the second time again. You get the limit as x goes to infinity.
So with infinity, you're always approximating because you can't really quantify the infinite.
Yeah, I mean, when we say infinity, that just means like grows without an upper bound. It just keeps getting larger and larger and larger and larger. And so we would just say the limit, the limiting value. There is no finite limiting value, so we've got to call it something. We just say infinity. It's like what's beyond all the numbers, in a sense. Okay.
But isn't it also true? Isn't it also true if the denominator has a lower x value, like its highest value is lower than the numerator, it would be the answer would be infinity, whereas the vice versa, it would be 0.
Okay, jumping ahead. That's okay. We'll do that on the next slide, I promise. Let's just finish this one off. I know that I'm like, come on, man, catch up. You're slow. Can't see, let's move it. But take the derivative of the top is 2, the derivative of the bottom is 6. And so, yeah, the answer does end up just being a third. You know, 2 over 6 is a third. So we would conclude by saying that the limit as x goes to infinity of x squared minus x plus 4 over 3x squared plus x plus 1 is a third. Go through that Lhopital process twice, confirming each time that you have the correct indeterminate form. On the homework, you guys will just skip this and they'll try Lhopital, and you're like, hey, it didn't work. Did you check? No, didn't check. Okay, so Lhopital's rule may not apply.
Is this just a special case? But since the highest values, which is pretty much 1x squared and 3x squared,
No.
that it pretty much tells you 1/3 right there, or a special rule that happens right now, or is it an actual process?
Right. So when you did this before, whenever you did this, probably in pre-calc or calc 1 or something, you see it was x squared minus x plus 4 over 3x squared plus x plus 1. Here's kind of two ways we could go about it. What you could do is you could multiply the top and the bottom by the same thing, and here's what it is, 1 over x squared. You multiply the top and the bottom by 1 over x squared, and this whole fraction distributed through will become 1 over x, and 4 over x squared. The bottom will become 3 and 1 over x and 1 over x squared, like that. So now if you take the limit as x goes to infinity, all you need to know is that whenever you divide by an x and you plug in big numbers, they're going to go to 0. So individually, that term is going to get really small. That term's going to get really small. That term's going to get really small. That term's going to get really small. And you're only left with 1 and 3. And the answer is 1/3. So that's one way to do it. The other way is just to say that x squared is, maybe I shouldn't say is, but x squared grows much faster than the negative x in the 1 part. So on the top, this is what's a process of called dominating terms, or dominating terms, is you really don't need to look at terms that aren't contributing much. So if one term is really much bigger than the others, then you can really just disregard the small ones because they don't contribute hardly anything. So on the top, the x squared is the dominant term. That's the numerator. In the denominator, what's the dominant term? 3x squared dominates x plus 1. So really, in the end, this limit is the same as if you just wrote x squared over x cubed and then just sort of ignore the rest. And the x squared would cancel and you'll also get to the third. So over time, you'll start to look at things that are how fast they grow. So now finally back to maybe Travis's question. Limit as x goes to infinity. If you had something like x squared plus x plus 1 on the top, and the bottom was 6x cubed minus x squared plus x plus 1, then we'll try this both directions, but if you looked at the dominating terms, what are the dominating terms? The dominating term on the top is x squared. The dominating term on the bottom is 6x cubed. And the rest of the stuff is going to be much smaller. So if you tried that limit as x goes to infinity, well, you could cancel some x's out, or you could even look again which one dominates between the top and the bottom now. X squared is getting really big, but x cubed is getting really big even faster. So you're dividing by numbers that are getting much, much bigger than on the top. And anytime in a fraction you divide by much, much larger numbers, that ends up being 0. So the shortcut is if the big number on the power is on the bottom, you get 0 for your answer no matter what. And you can see this through Lhopital's rule. We'll just do a couple of these. Lhopital's rule, again, you're going to look like infinity over infinity. The top is getting really big, the bottom is getting really big. So if we try Lhopital's rule on this, we get 2x squared, 2x plus 1, and 18x squared minus 2x plus 1. That's an infinity. We look again. The top is getting really big. The bottom is getting really big. We also look like infinity over infinity. Just let me finish this one off real quick. And then I tried Lhopital's rule again. So it's the derivative of the top, which is 2, over the derivative of the bottom, which is 36x minus 2. Now, if I plug in bigger and bigger numbers into this, the top is 2, and the bottom is getting really big. So if you divide 2 by a really big number, that limit is 0. And so you could have done it that way as well. All right, what's the question?
So I'm just curious, why focus on the dominating terms? I see there's a correlation between the answer you've gotten and the dominating terms value when divided over the infinite limits found. But just curious, why focus on them primarily?
The dominating terms just kind of is a shortcut to doing, it's even more of a shortcut than the Lhopital's rule is for computing. You only look at the terms that really matter, and then those terms are going to drive all of the behavior and therefore going to drive what the answer actually is. So I think this is another one that's an example of that.
So
yeah.
I'm just curious though, I mean, it just seems as if that's just a really easy way of doing it. I mean, are there any flaws in that method at all or anything potential mishaps or wrongs that could end up happening just focus on dominating terms?
It's always easy to make mistakes of any kind, but I would say that's if you know which terms dominate the others, then you just use those. You just straight up use those.
Okay.
So x cubed dominates x squared for sure. X to the 10th is going to dominate x to the 9th, 8th, anything below that. So if you're just comparing polynomials, you really just look at the highest power one and go from there. If you're not talking about polynomials, now you're talking about maybe exponentials or logarithms or who knows, square roots, something like that. What's happening in this problem? If you plug in big numbers into E, you take big numbers and plug them into X and cube them, both of those are going to result in really big numbers. So it does look like the top is getting really big or going towards infinity. It also looks like the bottom is going towards infinity as well. So which term is dominant? Is it e to the x or is it x cubed?
E to the x, because say if you put 1 in, you're going to get your 2.7 versus 1 cubed, and it will still be getting bigger.
Because x is infinite and cubed is not. 3 is not.
But the key is we're not looking at numbers like 1 or 10 or anything small. We're looking at like 10 to the 6th, 10 to the 9th, 10 to the millionth power. Really big numbers. So we want to go way out on the x-axis. Which now you're talking about things like e to the 10th versus 10 cubed. Like which one is bigger between e to the 10th and 10 cubed? Well, you can calculate that. But now what's the difference between e to the millionth power divided by a million cubed? Like which one is bigger? And over time you just kind of have to, I don't know. We'll tell you the answer in a second, but it's like you look at that, you're like, wait, this means a million times a million times a million, right? Because it's a cube. But what does this mean? It means e times 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 e, a million times. So we're talking about like a number that's close to 3 a million times versus a million 3 times. Maybe, I don't know if that helps figure out which one is which. I don't really care what this one is because n is too small. I don't want to plug in 10. I want to plug in big numbers. But anyway, the dominating terms is good if you know the order of the dominating terms. But for this one, it's actually pretty easy to just use Lhopital's rule. It looks like infinity. It looks like infinity. It looks like infinity over infinity. And so that is an indeterminate form that Lhopital's rule will kick in. So I can use Lhopital's rule. And we get the derivative of the top, which is e to the x. And we get the derivative of the bottom, which is 3x squared. Try again. Well, if we plug in big numbers to the top, I already know that goes to infinity. 3x squared goes to infinity. It's not quite as, it's certainly not as fast as x cubed, so I've kind of lost some power on the bottom here. Maybe pun intended, I didn't use it. Then it's still infinity over infinity. So I can do Lhopital's rule again. And I'll get the limit as x goes to infinity of e to the x over 6x. Okay, that's infinity over infinity again. So try Lhopital's rule again. I get e to the x over 6. Okay, shoot.
So whenever the limit's infinity or 0, just form derivatives on the denominator and numerator until the denominator no longer has an x values in them.
Well, in this case, that's true. That's true.
In this case?
You continue to use the process until it's no longer an indeterminate form, and it's one you can actually calculate.
It sounds like, well, I mean, it just seems like every example we've done is like that. I'm just wondering, because I can't really think of a problem that isn't like that, has an x on the denominator that's definite with an infinite or 0 limit.
I mean, for this one, for sure. I mean, if you have an e, the e will continue, the x's will disappear out. And then what is this final limit? The answer is infinity. Because I still have this E, which is getting really, really big. So the original problem is just plus infinity, because e to the x is a dominant term, or you can say dominates all polynomials. I mean, initially you might have a polynomial that's like x to the 100. That's going to take off, and e is going to be slow. But after a while, e is going to catch it and take off. And for big numbers, e to the millionth is, your calculator will say, forget it. I'm not going to give you the answer. It's too big. It'll be error divided by 10 to the 18th, which is possibly an error as well. So you can't really use your calculator on this problem either. So anyway, let's take a quick break, ponder some questions, and we'll come back and we'll do some other indeterminate forms and see how that leads into the next section while we listen to some of Kyle's music.
I barely understand what you're saying.
Yeah. 5 minute break, we'll come back. So